Today we're going to continue our discussion about functions with the concepts of boundedness and symmetry. When we're working with boundedness, we need to think about the range. Our function could be bounded above, bounded below, it could be completely bounded, or it can be totally unbounded. An example of a function that's bounded below would be something like this. I'm going to draw in this. This is probably something along the lines of y equals something x to the fourth, because there are 3 turning points. Clearly, there is a bottommost point on this roller coaster ride. There's some point at which the function is going to bottom out. An example of a function that's bounded above would be maybe the reflection of that graph. So maybe something making like this W shape, or M shape. I mean, not a W, but now it's an M. This might be something along the lines of y equals negative x to the fourth. So clearly we have in this graph a ceiling, or a topmost point. There is a point where this function definitely is going to top out and not go any higher than. Some functions are bounded. An example of a bounded function would be something that maybe did this. It's constant for a while and then took a jog and then constant again. This is a constant, or a bounded function, I mean, because it definitely has a ceiling and it definitely has a floor. It is bounded. And then finally, something that's unbounded would maybe be something like the cubic function, like so, y equals x to the third. And it's unbounded because it goes off towards positive infinity and to the right, and off towards negative infinity to the left. There's no lowest most or highest most point. So those are our 4 types of boundedness. Let's take a look at these examples over here, 1, 2, 3, and 4. I'm just going to make a really rough sketch, and then we'll talk boundedness. So y equals 2 minus x squared. The negative x squared tells me that this is going to be a parabola opening downward. That is going to have a topmost point, so I would say that this function is bounded above. Now, y equals 2 to the negative x. I'm not sure what that's going to look like. Well, probably a table of values would help me. So let's just make a few. Let's make a quick table. It's been a while since I made a table. Well, if I plugged in -2, I would get 2 to the -2, which is like 1 over 4. If I plug in -1, 2 to the -1 is like 1 over 2. If I plug in 0, I'm going to get out 1. If I plug in 1, I'm going to get out 2. No. Oh, I've got this all backwards. Oh, erase, erase. Oh no! Okay, back up with me. Okay, try that again. So because I'm plugging in a negative number into something that is already negative, this is going to give me 2 to the second, which is 4. This is going to give me 2 to the first, which is just 2. 2 to the 0 is 1. And then now I'm ready to plug in that positive 1. So if I plug in positive 1, 2 to the -1 would give me 1 over 2. And if I plug in positive 2, 2 to the -2 is going to give me 1 over 4. It's kind of a sideways 1. Okay, so what's this going to look like? Let's come over here. If I went to -2, I'd be up at 4. If I plugged in -1, I'd be at 2. Over 1, or over 0, up 1. Over 1, up a half. Over 2, up a fourth. So this is an exponential graph that is decreasing along its entire domain. Okay, so this, though, we can see is going to be bounded below. In terms of like a horizontal asymptote, it approaches 0 as x heads off towards positive infinity. Also, I notice that as I go down this table of values, my values are getting closer and closer and closer and closer to 0. So bounded below. Now, y equals 4. I'm going to change colors just because this is getting a little crazy in here. Y equals 4 is going to be the horizontal line through 4, like so. Now, it's never going to reach a maximum point, and it's never going to reach a minimum point. So number 3 is just straight up bounded because it is bounded above and below. And then finally, let's go on to number 4. This 4th example we already kind of talked about. Negative x to the third tells me that there will be 2 turning points, and I'm going to end on a negative note. So that's the graph of a rough sketch, approximately. I'm thinking about this. This isn't like my my answer. My thoughts tell me that I'm going to be completely, though, unbounded. This is an unbounded graph because I can get out, really big positive numbers. I can get out really negative numbers, really big negative numbers, a 0, anything. This is a bounded function for number 4. Okay, so again, I apologize for my flub up in number 2, but we've got a good example of all different types of boundedness. Let's go on to talk about symmetry. So with symmetry, there are 3 types of symmetry. There's y-axis symmetry, x-axis symmetry, and then symmetry with respect to the origin. I'm going to take a minute and I'm going to fill in a table of values for this function. My function being y equals the absolute value of x minus 2. I'm going to fill in values for -2 to +2, 1 and 2. So here, if I plug in -2, -2 minus 2 would be 2 minus 2 or 0. If I plug in -1, 1 minus 2 would be -1. If I plugged in 0, I'd just be left with -2. If I plug in +1 and subtract 2, I'd be at -1. And if I plug in +2 and subtract 2, that's going to give me a 0. All right, let's sketch this graph. I'm going to go to the left 2, up 0, left 1, down 1, left 0, down 2, right 1, down 1, right 2, down 0. Connecting the dots, I get this V-shaped graph, which is bounded below. I am clearly reaching a minimum point. This is bounded below. And the other thing, though, that I noticed that's maybe a little bit more telling are these points right here. For example, this point and this point. So what are the addresses of those 2 points? Well, I have -2, 0, and then over here I have 2, 0. Other points that are kind of fun to look at would be this point and this point. What are those points? They are -1, -1, and 1, -1. So what I see is that for x's, I get out y's, and then if I go with a -x, I'm going to still get out the same positive y. So when you are symmetric around the y-axis, this is a function that's even. So a -x gives you y, and then that positive x also gives you y. So remember that f of x is a fancy name for y, but when you have x and y, and then -x, and the same y on the same graph, that's when you're looking at a situation where you have y-axis symmetry, and we call that a function that's even. We call that an even relationship, even symmetry, even relationship. Okay, now let's take a look at this next function where we've got x equals y squared plus 2. So x is equal to y squared plus 2. Now this is kind of different. I'm going to input my y's and I'm going to get out my x's. I'm still going to plot this on the normal xy axis, but I'm going to plug in my y's, -2, -1, 0, 1, and 2. And let's see what I get out, or what am I going to get out for x. So x will come from -2 squared plus 2, which would be 6. And then -1 squared plus 2, which would be 3. And then 0 squared plus 2, which will be 2. 1 squared plus 2 would be 3. 2 squared plus 2 is, now I'm back to that 6. Let's plot those points. I'm going to go over 6 and down 2. And then while I'm at it, I'm also going to plot this ordered pair here over 6 and up 2. Then let's plot over 3, down 1, and over 3, up 1. So I just plotted this point and this point. And then let's go over 2 and up nothing. That's this point right here. When I connect the dots, I get this sideways U shape. I get a sideways parabola that's opening to the right. Now, this isn't a function. It's not a function because it doesn't pass the vertical line test. It will not pass the vertical line test. But what we can say is that since xy and x negative y are on the graph, we can say that this is a relationship that kind of creates, it's symmetric about the x-axis. All right, so again, it's not a function because it doesn't pass the vertical line test, but when x and y and then x and its opposite y are on the same graph, you're going to be looking at some symmetry there about the x-axis. Now, the last kind of function to talk about in terms of symmetry is an odd function. So you're going to have an odd function if your input and the opposite of the input give you the same values. What? Okay, let's take a look at our inputs of -2, -1, 0, 1, and 2. Again, looking at this function here, I'm going to input x and I'm going to get out y. So when I plug in -2, -2 to the third power gives me 8 and -8. -1 to the third power gives me -1. 0 to the third is just 0. 1 to the third is 1. 2 to the third is 8. And then this was 2 to the third power. So let's plot those points. Over -2, here's -8. Over -1, down 1. Over 0, up 0. Over 1, up 1. And then let's go over 2 and go up 8, so up to 8. Well, this is a cubic function. I recognize that. It's going to look something like this. And this is a pretty cool odd function because look at some of these points. We have -2, -8, and then 2, +8. So this is when we have odd symmetry. Another way of thinking about this is if both things are opposites, if you have two opposites, or in other words, if both are opposites, then you're looking at odd opposite. So -2, -8, and 2, -8. Those things represent odd symmetry. All right, and then lastly, let's take a look at this function right here. F of x is equal to 3x to the third over the function, the quantity x squared plus 1. So is this function odd, even, or neither? I have no idea what this graph might look like. So what I'm going to do right off the bat is I'm just going to pick some arbitrary point, like maybe 1 and then -1. So if I plug in 1, what is f of 1? F of 1 would be 3 over 1 plus 1, or 3 over 2. So I get out 3/2. Now, let's plug in -1. So if I plug in -1, 3 times -1 to the third power, and then -1 squared plus 1, that's going to give me -3 over 2. -3 over 2. -1 to the third power, remember, would be -1. -1 times 3 is -3. Okay, notice that both my x's and my y's, x and y, are opposites on both accounts, on both the x side and the y side. Therefore, this function has odd symmetry. We would say that this is a situation where we have odd symmetry. And then if you're not quite sure, like, could you verify this for all points? Just for the fun of it, let me prove it to you. Let's look at f of 10 and f of -10. So I'm going to do +10 and -10. Well, when I plug in -10, this would be like 3 times -1000 over 100 plus 1. So -3000 over 101. And then when I plugged in +10, this would be 3 times 1000. So 10 to the third is 1 and 3 zeros over, again, 100 plus 1. So we're looking at 3000 over 101. We still end up with opposites. Opposite x's give us opposite y's. Odd symmetry. Okay, that's it.